We're back. And I'm actually kind of excited because we're going to learn something new. I think I'm kind of getting to introduce it to you. I don't believe it was an AP Physics 1. I know it wasn't an EP Physics. And there's a little bit of a surprise maybe if you don't know this stuff already. We're going to start learning about chapter 26 about magnetism, magnetic field. So, magnets do stuff too. Not just electrical charges pushing things around or pulling on them, but magnets can do that. And I think you learned this stuff way long ago probably, that magnets have poles. There's like a north pole and a south pole. And why would you name them that? Maybe you know it has to do with compasses. The history of this, I need to read up on a little bit more, but I understand that actually this was discovered first in China, I believe. And there are naturally occurring rocks. I didn't bring it home with me. I have a rock like that called a lodestone. It's a naturally occurring magnetic rock. It picks up little pieces of metal. That's neat. That's all magical and everything. You remember how, like with electricity, the word electron actually was a, I think I said this, was a Greek term for amber, the precious, like, petrified sap stuff. You polish it up with your cloth and it pick up little bits of grain or cloth or whatever you had laying around. Well, these lodestones, these magnetic rocks, would pick up metal. And not only that, but if you did something like, I'm not sure how the first way it was done, but you could maybe put one on a little raft or hang it from a string, and it kept orienting itself the same way every time you gave it a chance along geographical lines. North was already a meaningful thing because, the North Star and the way the sun rises and sets and all, astronomically directions had already been known. But then these rocks would line up with the astronomical north and south. And of course, you would call, if you had any sense, you'd call the end that was pointing north, north. And the end that was pointing south is south, obviously. But you also discover when you do these things that the opposites attract and the likes repel. And I think you know this. You take a north pole of a magnet, put it near another north pole of a magnet, they repel. The north pole next to a south pole attracts. So think about it for a moment. What kind of a magnetic pole must exist up, where Santa Claus lives, at the Earth's geographic North Pole, near it? Think about it. The north end of a magnet is attracted to it. Ironically, up here, they bothered to point it out, somewhere up here, it's in here somewhere, is a south magnetic pole, which you might call the Earth's north magnetic pole because it's up north, but you see it's a south magnetic pole. I think you can figure that out. In any case, so magnets play this game that's analogous to the game that charges play, where positive charges repel positive charges and opposites attract. And here, same sort of thing. But I'm going to raise a question here. There, I'm going to raise a little question. Before I do that, I said magnetic field. Remember how Michael Faraday imagined these lines that he could draw. He liked to draw because he didn't go to school very much, and so he was kind of artistic with it. So, electric charges are imagined to have a field pointing away from them, an E field. Okay. So I guess magnets have fields too. Well, you can see these fields in a way. You can visualize them. And I did not bring home, I grabbed all this stuff and didn't bring this one with me. There's a magnetic field demonstrator sort of thing where you can put a magnet and have a container around it with oil with floating bits of iron in it, little iron filings. And what they'll do, they'll line up and they look like they're tracing out lines like this as they orient, the little fibers orient themselves along lines. And in fact, we're going to define the magnetic field, the way those little things line up, and say that it points out of north poles and into south poles. Now, the meaning of this field is going to become evident in just a moment. But right now, I'll just say there are magnetic fields, and you can sort of trace them out with iron filing, so they're kind of real. You know? So let's just say we have a north magnetic pole, and it has supposedly mysterious field lines sprouting out. Oh, the letter we use, I'm sorry, it's not an M. For historical reasons, I've actually forgotten. I looked it up once, and I think I forgot. It got called B. So B is the name of the magnetic field. It has a magnitude and a direction, and we're going to talk about the units and all that very shortly. So in any case, what if we had a north magnetic pole here, and we had magnetic field lines, whatever the heck they are, sticking out of it? What do you think would happen if I placed a positive electric charge in that magnetic field where this north magnetic pole is down here, and here's a positive electric charge up here? In class, with some interaction, I like to make people guess. I'll pause briefly so you can try to guess what do you think happens to that charge in a magnetic field that points that way. There, maybe you have your answer. Sorry, I can't ask you. Some people think it repels it. Nope. Oh, then it must attract. Nope. What does it do? Nothing. It's oblivious to it. It's like they're two different kinds of things. You know, should a, male dog be attracted or repelled from a female cat? Probably neither. They're not the same thing. So the first thing I'll say is magnets are not electrics. They're different things. And so it shouldn't respond. But wait, you're taking a sub-course here called electricity and magnetism. You've probably heard of electromagnetism and electromagnetic waves and stuff like that. And magnets are used in generators that generate electricity. You can make an electromagnet by wrapping wire around a nail and running a current through it. There's a connection. Oh, there is. It's just kind of a surprising one. The connection is, I'll tell you, I don't know if you saw Jurassic Park or not. There's a scene, the original Jurassic Park, there's a scene where the little bus is turned over and the T-Rex is looking in, and the Jeff Goldblum character says, "Don't move. If you can't move, if you don't move, she can't see you." I don't know how you know that from a T-Rex skull, that it couldn't see you if you didn't move, but let's just pretend it's that way. I've heard frogs can be that way. I've heard that frogs can starve while looking at a juicy fly because the fly didn't move. And when it moves, all of a sudden the frog gets it with its tongue and all that. If this thing moves, things change. Like, for example, what if this thing moves to the left, has a velocity to the left? Then I'm telling you, the magnetic field now exerts a force on it, but in what direction? Once again, I could make you guess. Tell you what, though, let me tell you some directions that just kind of aren't fair. It wouldn't be, I don't know, I can't see any reason that a magnetic field pointing this way would make something moving this way move more that way or less that way, or it's got to be something we pull out of the hat. I'll tell you what it is. It's a thing you're going to have to use something called the right-hand rule. There's different versions of the right-hand rule. Different teachers, you do different naming things and everything. You use your hand. You could do a left-hand rule and switch things around or whatever. Here's mine. It's the one I like. Let's rename your little friends here. This is now your VUMB, with a V, VUMB. That's what it stands for. Velocity. These are your bingers. They stand for the magnetic field. And what do you do with your palm? You push. So we have a positive charge here. So I'm going to use your right hand. I'm going to take my VUMB and put it directed this way, my fingers that way, and my palm pushes into the board. This charge will get pushed into the board by the magnetic field that points this way when it moves that way. Weird. Now, if I had made the velocity this way, my thumb would have pointed that way, and I'd have to twist my hand around, and then my palm would push out of the board. Guess what? If it's a negative charge, you can either reverse the direction that you get with your right hand. If you want to be really cute about it, you can just use your left hand for negative charges. Whatever, you get the idea. Let's play with that a little bit more. The problem is I have a two-dimensional thing to draw on here, and we're talking about something that involves all three dimensions of space here. I'm going to introduce a symbol, a couple of symbols. Imagine some kind of flying arrow thing that has a painted tip on it and like a turbofan engine in the back, some kind of X-like thing in the back. If it was coming at you out of the page, out of the board, you would just see the tip looking like that. If it were flying into the board, you'd see the tail end of it looking like that. Actually, when I first was learning physics, we tended to draw the whole circle and everything, and this is why I got lazy. And now we just put dots and X's. So if I draw a bunch of X's, I'm talking about some bunch of vectors that stick into the board. And a bunch of dots means it sticks out of the board. You know, like that would be sticking out of the board. So let me try another one of these examples. Let's say we have, let's say this is the B field. Now, these X's are often used, usually used, to indicate the direction of the magnetic field, but they can be used to indicate a velocity. So in other words, you could have a V that's an X because the velocity is into the board, or even a force could be in or out of the board. So it's just a generic thing for in or out of the boardness. But let me try this. I'm gonna have let's switch around. Let's have a negative charge moving downward toward the floor in a B field that points into the board, and see if we can do this contortionist stuff to figure out the direction of the force on it. Okay, so I'll use my left hand because it's a negative charge, I guess. I mean, you know, use your right hand and switch it if you like. But I'll use my left hand. I get my thumb pointing down. Uh-oh, this is going to be twist around. My thumb points down, my fingers point into the board, and my palm pushes that way. So the force on this moving charge is going to be, I think I just said, that way. There's the force on it. So again, right-hand rule for finding the direction of the magnetic field, or the magnetic force on a charged particle moving in a magnetic field. So that's the direction stuff, and it's kind of weird as it is. Oh, forgot to mention something important. What if it moved this way? Then it kind of closes your hand up. Your fingers and your thumb come together. Imagine that makes you weak. Imagine to be strong. You know, your martial arts master or something teaches you that this makes you strong and that makes you weak. Same thing happens here. Of course, I have no idea that it really does that. But anyway, if the velocity is parallel to the field, there's still no force at all. If it's parallel or anti-parallel, no force at all. So what if it's at an angle? I think you know what happens. It's one of those component things where there's a sign of an angle involved. So really, it's the component of the velocity that's perpendicular to the field that determines how strong the force is going to be. And so now that we have the direction of this vector down, this magnitude of a force, sorry, the direction of the force, time to talk about the magnitude. Like, oh yeah, how much? Well, think about the things that matter. Surely, if this force only happens to charges, if I were creating the universe, and I did not, but if I were creating the universe, I think I'd do what they really did. I think I'd make it proportional to the charge. Why not? No charge, no force, some charge, some force. I think since non-moving charges have no force on them at all, I think the faster you go, the stronger the force ought to be. So if I were making the universe, I'd make it proportional to V. And it is. And then there's this magnet. Oh, wait. probably should have said V sine theta. I'll write that separate. I guess I'll write it separately. I could put it together. I could put the sine theta right after the V, so you know I'm just talking about the component that's perpendicular to the field. But I'll write it this way, sine theta, fair enough. But it also needs to be proportional to, guess what? The field, B. It needs to be proportional in strength to B. I haven't made up units yet. I will in just a moment. B is kind of, at the moment, like a figment of our imagination that we conjure up to, like, explain weird things happening. But here it is. And when you put it all together, F should be proportional to Q, V, B, sine theta. Okay? I said proportional to. I think you know proportional to means equals a constant times. So what's the value of the constant? The thing is, we have a golden opportunity here. If we want to, we can make the constant be 1, not because we control the universe, but because we control our choice of units for the thing that doesn't have any units yet. This is the one thing up here that doesn't have units. I mean, sine theta doesn't have any units, but here we got, you know, we got coulombs here, we got meters per second here, we got newtons over here, and I'm going to make some constant. I'm not going to call it K. You know what? We can make it up as we go. In fact, it should be the Newton second per coulomb meter. That should be the unit, shouldn't it? The Newton second per coulomb meter. Because that would cancel out the coulombs and the seconds and the meters, give you newtons. But of course, most of the time we want to name things after famous dead people. And actually this one you've probably heard of before. First name, he was Serbian, lived back around the turn of the last century. Nikola Tesla. Yeah, the cars Elon Musk sells. Somebody told me that Tesla invented the electric car. That's actually somewhat debatable. He did help invent alternating current electricity with Westinghouse. There's a big thing about Tesla and Westinghouse. And God, it's embarrassing on a video to forget. You know, Thomas Edison. Yeah, he wanted direct current. Whole big story about that. But in any case, debatable whether or not Tesla really invented an electric car. But he did get a unit named after him. This is called the Tesla. And as long as we make the Tesla be 1 Newton second per coulomb meter, we don't have to make up some new constant. We got enough constants swimming around in our heads anyway. So there we go. There's how strong the force is. It's QVB sine theta, where V is measured in Tesla. Now you might wonder, how much is a Tesla? Remember, a coulomb is like, in a way, this tremendous, crazy amount of charge if it's net charge, and yet I've got hundreds of thousands of coulombs of positive charge and hundreds of thousands of coulombs of negative charge in me. So, like, how big is a Tesla? I'll tell you what, those little magnetic rocks that, you know, people would find and they barely point north and everything, pick up paper clips, that's like it's like 10 to the minus 5 Tesla maybe or something when you're close in. The Earth's magnetic field, right where I'm standing, is about on the order of 10 to the minus 5 Tesla, a few times 10 to the minus 5 Tesla. Yeah, a few times 10 to the minus 5 Tesla. But those MRI machines where they tell you not to take your credit cards in the room and metal objects go flying and everything, those things are 1, 2, maybe even 3 Tesla. So Tesla's a pretty big unit of magnetic field. And it is what it is. So we figured that out. Now, there's another issue is we don't really very often deal with isolated moving charges. I mean, if you're shooting a proton through a magnetic field or an electron or something, then yeah, and there are problems we do like this. But the most common thing you're going to encounter in real life is not an isolated charge moving. It's a whole choo-choo train of charges, a whole conga line of charges moving, called an electric current. So what I'd like to do is come up with a relationship for a force on a wire that's carrying a current. I'm going to do it the quick, cheap, dirty way. I'm just going to say that if F equals QVB, and I know there's a sine theta, there's a sine theta that's understood up here, but if F is QVB, then I'm saying that that's like newtons equals coulombs times meters per second times Tesla. But notice I could just move the seconds over a little bit. It also ought to be true that newtons equals coulombs per second times meters times Tesla. It's kind of a cheap, quick, dirty way to do a derivation. I should really draw pictures and stuff, but it works. Yep, it's true. This is I. So what's the M? The meters. What does it measure? Guess what? The length of the wire. And then this is the magnetic field. So we have this F equals ILB. Yep, there's a sine theta. This is how hard a magnetic field pushes on a wire. Now you're starting to get some kind of realistic thing. You know, we could tell you what, it's not unusual for a wire to carry a current of 1 ampere. Like if I go make a piece of toast in here in a minute, there's probably like an ampere-ish kind of amount of current flowing through the toaster. So it'll shock you pretty bad. You have an ampere run through you. You don't want that. But it's common household stuff. Would have a current of 1 ampere. So you could do that. And what if you took your 1 ampere current and you took it in one of those 3 Tesla MRI machines? Let's see. And what if you had a piece of, I don't know, a half a meter long piece of wire with 1 ampere, and it's a half meter long, and you hold it perpendicular to the field, so the force is big, and we multiply that times, say, 3 Tesla, you end up with a force of, wow, like a Newton and a half. That would be palpable. So, in fact, it's like a few ounces, less than a pound of force, but it's a noticeable force. You can feel that. You feel some resistance, so to speak, in another sense of the word. So, yeah, that's that. Now, I want to continue just a bit more and talk about the motion of a charged particle in a magnetic field. Now that you know that it can push charges off to one side, let's see what happens if it keeps pushing charges off to one side. So I'm going to make up a magnetic field. I'm going to make one that points out of the board. That's what I feel like today. This magnetic field exists all over the place because there's some magnets around. You know, how do you make a magnet? Oh, that's next chapter. But anyway, this is the B field pointing out at you. So what I'm going to do is I'm going to take a positive charge. I'm going to take a positive charge and shoot it to the right. So I get my, is that what I wanted? Nah, I don't like where I drew it. Sorry about that. It'll work better. You'll see why. If I do it this way. So let me point it this way. Here's my charge. Here's my magnetic field. So I got a field pointing out of the board. My bum points to your right as you're watching here and pushes up. So this thing's going to get deflected upwards. But you know, if it curves upwards enough, it might one day find itself moving this way. And once again, fingers out of the board, thumb up, push this way. My goodness, the force is always perpendicular to the way it's going. I think you know what this is going to do? This is a centripetal force, and it causes it to go in an eternal circle. That's the natural motion of a charged particle in a magnetic field, to go forever in circles. Naturally circles because the force is always perpendicular to the velocity, and that's what that makes, a circle. More generally, it could be a helix because, well, think about it. Why could it be a helix? Right. It could be moving out of the board at you too, and then it'd be this kind of like, spirally thing like that. So helical motions are actually natural for charged particles moving in magnetic fields. What can we figure out about this? What's there to compute? Oh, well, how about the radius of the circle? What can we say? We can say that the centripetal force is the magnetic force, which I'll draw it like F sub B. So that's like mv squared over r equals qvb. I'm not going to put sine theta here because I'm already shooting it perpendicular to the field, and its sine theta is 1. Well, that's easy. You can find the radius from that. Well, one of these cancels out. You get a radius of mv over qb. Wow. Not bad. Now, all kind of interesting stuff all kind of interesting applications come up. I'm going to be talking about those. I'm going to try to keep this video less than half an hour today, though. So if you look at your book, there's a thing called the magnetic bottle. There is a velocity selector. There is a mass spectrograph, which is a very, very useful tool. And there's a thing called a cyclotron. I love the way that sounds. That's a type of particle accelerator. So those are some applications in the chapter. I think I've already posted the chapter 26. Well, if I didn't, I will. I'll be posting those very soon. So have chapter 25 in, at least by Monday at the very latest, and we'll get the rest of 26 done probably in the next video. So talk to you later. Bye.